So let's let the fun begin. Okay.
Oh, wait, you're recording this?
Of course. That's why I said let the fun begin. So the big goal of this, so much of quantum mechanics is pretty abstract. This is going to be kind of abstract, but it's useful. We know that energy is quantized. There's all these energy levels. Well, we're trying to get into spectroscopy now. And for spectroscopy, you have allowed transitions and unallowed transitions. Bless you, my goodness. So there must be we want to have some easy way to identify each energy level and to say, oh, you can have this transition from here to here. And this will be the wavelength and that sort of thing. This is my talking spot.
Too bad.
So what the goal is, that's the goal. It's pretty much to have a descriptor for every single energy level. And then by doing this right, we can assign transitions. Okay, so starting out, we talk about electronic structure. And I think when they say electronic structure, I'm thinking of stuff like, which atom was solved by the Schrödinger equation exactly? Hydrogen atom. It has all these solutions called orbitals, right, or wave functions. One electron wave functions, really, right, is what they are. So, and you can write those one electron wave functions, or you can just simply write 1s. And that's enough descriptors. There's enough quantum numbers there that actually assign what the wave function is. So when we write electronic structure, that's kind of what I'm thinking, right? And then you've got these one electron states, wave functions, and they just keep on going up, right, in energy. Okay. So, and we talked, you mentioned already that the hydrogen atom was solved exactly in the Schrödinger equation, but the point is not hydrogen. The point is one electron. Because the difficulty in solving this is in that Hamiltonian, you've got that part plus V, that potential energy, where you have all these different electrons. And their repulsions are really complicating things. So it's the one electron that really does the trick. The number of protons, really doesn't matter in the nucleus. So that's why they have this word hydrogenic. So all this stuff works great for things that are hydrogenic, right? Ions or atoms. Well, atom, hydrogen. The rest are going to be ions. Okay. And then so that's why they're distinguishing between these two. Mini electron atom, well, there's more than one. It'd be their mini electron atom. Oh, and I forgot have you guys seen the instrumental people have? But Jeffrey, Gloriana, have you seen the discharge lamp tube and you see the lines?
Mm-hmm.
You have.
That's really cool.
Have you seen it, Jeffrey?
I don't think so.
Oh, then I gotta go get it now. All right. Hang on, let me go get it. Or you know what? Let's just go over there. It'd be so much easier. Right? Because it's nice and dark over there. All right, come on.
Yes.
I was wondering what you're doing because I thought you just didn't want to open up your backpack.
I'm
You
gonna
were just like,
field trip. I'm gonna cut this one off. Sick of it. It's like the fourth time that's happened.
hydrogen atoms get dissociated. We saw their spectra, their emission spectrum. Was that an emission spectrum or an absorption spectrum, my instrumental people, that you just saw?
Emission.
Emission, yeah, you're seeing it. Emission intensity. Here's wavelength. So I don't know, you saw a red, I don't know, did you see an orange?
Yes. Yes.
Did you see a blue too or something?
Yes.
Here's a blue, here's a blue, right? So we see these different lines, okay? So now the book has a nice, I'm a little bit behind in this chapter. Usually I can get everything in the outline here. This is on page 344. Okay. So do you see these different lines? Okay, this is all just for the hydrogen atom. It's on page 344, figure 13.1. And some high school teachers actually figured this out. And they found out that there's this simple numerical relation between the different lines. And they were just playing around. And if you have in this relationship, if you have N1B1, what is that? N1B1, you get the Lyman series. So you get those colors. Now you probably didn't see this many colors in there. We need a lot better spectroscope and we need to really widen things out, the resolution and things, but there's a lot of different lines for the hydrogen atom. And if you make that little N1B2, you can get all the different lines for the Balmer series and the Paschen series. So these, I think 2 of these guys were high school teachers that figured this out. So it's kind of neat. What is this? So this is the Rydberg constant. That's just you just look it up somewhere. N1 and N2 are just our counters, right? Here's where N1's defined. N2 is just going to be 1, 2, 3, 4, 5, right? What's this guy? What is that?
R.
This thing with a little squiggly on it.
Oh.
That thing.
What is wrong with
It has, here's a hint. It very commonly, most commonly, has units of inverse centimeters.
frequency?
Wave number. It is a frequency, yeah, but wave number. Wave number. So let's jump ahead a little bit. This Bohr frequency condition. That's really what we were seeing. We're seeing these lines, and if this photon was emitted with this frequency, h is whose constant? Planck's constant. And you can get the difference in energy levels, right? It jumps down from one level, like right here. It jumps from one energy level to the next, and you kick out this energy, this specific frequency, and only that frequency. Okay, but let's get it in terms of wave number. How can I get this in terms of wavelength first? Delta E equals, how can you get wavelength in there?
Wouldn't you divide it by lambda?
There's a lambda down there.
And the speed of light?
Yeah, so the whole thing is,
So isn't it like C over lambda?
there it is, hc over lambda. Okay, now, we can get wave number in here. How are you going to do it? What is wave number has what units again? Most common units. Reciprocal centimeters, which is a 1 over a distance. So that means a wave number is really what in this equation? 1 over lambda. Perfect. Right? So we can write, how can we get wave number in here then? It would be what times what times what?
H times C times 1 over lambda.
H times C times 1 over lambda, but 1 over lambda is wave number. So R delta E,
Oh,
HC, wave number. I'm trying to make that little tilde. Not very good at it. You know what I'm trying to draw this thing. Okay. So And the Ritz combination principle is really the big picture for this entire chapter. Okay? What we're going to do is we're going to assign a term symbol that describes this state. We're going to describe a term symbol that describes that state. Now this term symbol, it needs to take into account, what the energy is, but even more so, especially things like angular momentum, because angular momentum is really going to be the key as to whether you can sink from one state to another state, right? Because we know that transitions can only occur between these different states. So if we write the term symbols correctly for every single state, we're going to be able to look at them and say what transitions occur, what the energies are going to occur, which transitions are not going to occur, and all those. Okay. Now, for my instrumental people, if a transition cannot occur, does it occur anyway? And if so, what is it called?
I want to say it does occur anyway, because it's called something.
Yeah, because impossible things happen at the quantum mechanical level. So yeah, it's always safe to say impossible things happen.
I don't remember what it's called. Did we just learn this? Was it a while back?
It's when light is emitted, it starts with a P. Phosphorescence. Glow-in-the-dark toys are all happening because of energetically impossible things that are happening. So it's crazy. That's why you can see them, though, because otherwise that light would be gone in nanoseconds or faster, picoseconds, 10 to the 1,000th of a billionth of a second. Okay. So that's the big picture. It's the Ritz combination principle. We want to assign term symbols for all these different states and then talk about everything we talked about, transitions, all that kind of stuff. Okay, so let's see if we can get there. We're not going to get there today, I don't think. This is just kind of like fundamental stuff. So the structure of hydrogenic atoms. If you have a hydrogenic atom or ion, what do you have? You really have two things. I'm talking about this actual system here, this atom or this ion that's supposed to be hydrogenic. What two things do you have? What make up this hydrogenic atom?
Charge?
Yeah, more specifically, what is charge of? Okay, you're going to have an electron. Okay, you're going to have an electron. Because hydrogenics, they want it like hydrogen. So that means you got to have one electron. They want it like a hydrogen atom. And then you also have a proton. Or more, right? It could be, you could have, I don't know. Helium has how many electrons? Usually 2, right? So let's make it hydrogenic by giving it a +1, all right? So the number of protons, I would just say nucleus. You got this heavy nucleus. Now I say heavy, are you sure that's heavy? What's more massive, a proton or an electron? By how much? Did you ever look at this? Yeah, it's around 10,000. Protons are about 10,000. You just look at the inside front cover. They're about 10,000 times more massive than an electron. So you have this really heavy nucleus compared to this really light electron. So let's say M1 is my electron, and M2 here is my nucleus. What was this mu called again? It says on there. Reduced mass. Okay, this is in the concept preview. M1 is much, much lighter or much, much heavier than M2? Lighter. So remember, you're supposed to write something like double arrows. That meant much, much. Remember doing that kind of thing? Okay, well, now you did. So M1 is much, much smaller than an M2. The reduced mass then really comes out to be what then? Surprisingly, I think it's surprisingly, M1. The reduced mass is M1. M1, we said, is the mass of a electron. In these problems, reduced mass is just the mass of an electron. Well, why are we talking about reduced mass in the first place? This is a general physics question. if I'm going to throw a baseball across the field, I don't know why, I can't think of anything else besides baseballs. I'm going to throw
Tennis ball.
a tennis ball across the field, right? Or the guys are out there right now. First tennis match at the lake is going on right now, and we are missing it
I saw it.
because
They're
we are
going doubles
here.
Right now. They're going doubles right now.
So anyway, where was I going with this? Oh, why use reduced mass? Like you have all these equations, a tennis ball is flying through the air. Would you use reduced mass or just the mass of that tennis ball and all those physics equations?
Oh, a tennis ball. It was the mass of the tennis ball.
I guess we should make it more complicated. You have two tennis balls jammed together, right? Since you want more than one object, right? A big tennis ball and a ping pong ball jammed together, right? And they're hitting that thing back and forth. It's still just mass because it's just translational motion. Translation is just going from here to there. That's it. You don't care about the internal modes of this tennis ball, ping pong ball system, right? Oh, it's vibrating or it's rotating. No, we just care about it going from here to there. That's it. I just want to know its mass. That's all you need to know. But when you start talking about this kind of thing, what is going on? We're not talking about translation anymore. We're talking about this thing just sitting there. What's its internal motion? That's all reduced mass. You have to use reduced mass for those types of calculations. They probably don't hit on that enough in physics. Okay. But our reduced mass is kind of simple because our two objects, one is much, much lighter than the other one, so our reduced mass is just the mass of an electron. It's kind of nice. Okay. The Bohr radius. What was Bohr's big deal? The Bohr model of the atom. What was this? Do you remember this? Historically speaking, you had the plum pudding model, and you had the Rutherford's gold scattering experiment, and you had the Bohr model. Don't you remember this? Jeffrey, you don't remember this?
I don't know what you're talking about right now.
You had general chemistry from me, young lady. You should know this.
That was like 3 years
Okay.
ago.
So Bohr's model of an atom was this. You had the nucleus. Okay, and we can be in this orbit, or we could be in this orbit, or we could, see what I'm doing?
Yeah.
Or we could be in this orbit. Okay. Now, there's no way you can get that to work and describe all the things that are going on with spectroscopy and with colors of t-shirts and with light scattering off of surface. You just can't describe the interaction between light and matter with that type of model. It doesn't work. But it's really, it's so useful because look at that. We can jump from this. First, it has the quantized energies things down. And you can jump from this energy level to this inner one. Ooh, give off a photon, right? And it's going to be exactly between those two energy levels. The Bohr model of the atom is really messed up by what that we've talked about? What just throws this thing out the window?
Jumping around. Or maybe some more orbitals.
It was a technical jargon for this. Somebody's principle just throws this out the window. Heisenberg's uncertainty principle, right? You can't know the trajectory of an electron. You can't know its orbit, that kind of thing. You just know this. Hey, 90% of the time it'll be here. This isn't what it looks like. This is just saying 90% of the time it'll be there. Experimentally, you'll find it there. Okay. Where am I? Oh, I was talking about the Bohr model. Okay. So the point is it's just kind of hung on, so we still like to think about it, I guess. But for this hydrogenic atom, the most probable distance is r, which is, they call it a naught, the Bohr radius. And we kind of did this in that concept preview already. We came up with this, but you didn't know what it meant. Okay, and how many meters is that? It was like PM. What's a PM? This is the most probable distance an electron is from the nucleus of a hydrogen atom. It's 52 PMs. P stands for
Pico.
pico, which is 10 to the negative.
9.
Negative 9 is nano. So add 3 more.
Negative
Negative 12. Or subtract 3 more. Negative 12. A thousandth of a billionth of a meter. Okay. So this hydrogenic atoms, we solve the Schrödinger equation with them exactly. We come up with all these one electron wave functions, right? And wave functions. Or I don't think we ever in general chemistry called these one electron wave functions. We said orbitals. Hydrogenic orbitals, hydrogen orbitals, right? Solutions to the Schrödinger equation. But they're really just one electron wave functions. Okay. Page 361. Again, I don't have all this in there. What was I trying to get at? Oh, okay. So they're trying to say, this is on page 361, they talk about this, that, okay, what if you have this, I'll just write it down and I'll talk to you about it. And this keeps going. If you keep multiplying them together, that you can get this overall wave function just by multiplying these individual wave functions. And very often, these individual wave functions are just what we're used to seeing: 1s, 2s, 3s, that kind of thing. So R1, right, 1 electron, just its radius, R2, its variable for its distance. And they're just trying to get us into seeing, hey, we're not going to always be working with hydrogenic, but many electron atoms. Okay. But the point with this stuff, this quantum numbers, remember this n, l, and m sub l? N could be what? When we don't want to go and solve all this stuff. We just want to use the results. In these quantum numbers, n could go from 2, 3 on up. And then you had L.
And -1. Or 0 to -1.
Yeah. Well, -1 to 0. Right. And then we had, and that could go from, yeah. Okay. So there's our quantum numbers for our solutions for hydrogenic atoms for the Schrödinger equation. And then we talked about how in the concept preview we did this. We said that we could start listing them all out. We could start saying, and we did this in the concept preview, so that's why I don't have to do it now. Number of orbitals, and then like if you had 1s, 2s, 2p, you start listing them all out. 3s, 3p, 3d. Remember how this worked? It was always what squared?
N squared.
N squared. So this would be 1 squared, 2 squared, 3 squared. It's always the number of orbitals. N squared. Good. For any L, there are how many orbitals? If you pick an L, how many orbitals do you get out of it? Like if you pick L equals 1,
0 to n-1, so 4.
no, well, where I'm getting at is, think of like 2p. How many orbitals did you draw?
3.
3.
Well, that's 1.
So that's for L equals 1. It always works out this way, 2L plus 1. It's the number of different what values? M sub L. That was the number of different orbitals that you had. Okay. For any given L. For L equals 2, you'd have 5. So that means in the D subshell, you're going to be drawing 5 orbitals. Okay. We'll be messing with that some more, but hydrogenic. So we're supposed to have how many electrons again? 1. But the Z, I just answered it. Z is the atomic number, exactly. So we don't have to have 8ZB1 and be talking about hydrogen all the time, but we need to be talking about hydrogenic, so we only have 1 electron. So it looks like the energy is dependent on what quantum numbers then? Look at this expression. We just mentioned a bunch. We mentioned, and we didn't even mention M sub s, but what quantum number is the energy dependent on? N and solely N, or these heterogenic atoms and ions. Okay, solely dependent on N. Because you give an N, you know the energy. Okay. You can kind of tell here. I mean, there's one little subscript on the N. Oh, hey, this is kind of interesting, I think. So energy is only dependent on N. Look at that. Every single energy. Do you see a way to get positive energy out of this? Knowing what you know about H, C, Z, and this Rydberg constant?
Is it right or negative?
There's no way you can get a positive number out of this, right? There's no way. This, again, is general physics. This negative energy meant something. In fact, you very often had to put the negative sign on there, I think. Well, maybe you didn't. No, maybe you didn't. I don't remember the entire expression. Q1, Q2 over R. Remember, I don't remember the exact equation. I want to write it. That potential, electrical potential energy. And we had to show in the concept preview that had units of joules. But the point is in the numerator of that, you have Q1 and Q2. So we have an electron and a nucleus. One is negative, one is positive. So you multiply them, you get a negative answer. So that's their convention, and they're sticking with it. This is one is negative, one is positive. We're talking about attractive or repulsive electrical force. Attractive. So their convention is attractive electrical force is negative. That's why this guy is always negative. So the deeper down you go in the well, the more negative energy you have. So it's not, negative energy in the sense, right, cancel out other type. No, it's just a way of expressing energy that's attractive in nature. So the very top, right, E equals 0. Right, here's where E equals 0. And it gets more negative as you go down and deeper into the well. Okay. Okay, so here's our energy levels, right, for this hydrogenic atom. This says classically allowed energies. I don't know if you can read yours better than that, but this says classically allowed energies. So they're just trying to say, classical. Well, classical means what? The size of our tables and us, right? Yeah, you can have any energy you want. So I don't know why they even have it there. We know that. But what's kind of interesting is they're saying classically allowed energies is also up here, above where energy equals 0. A continuum. So now they have H plus E minus. They're free. It's ionized. So does that mean that, is this thing physically telling us that you have a hydrogen ion and an electron flying around totally free and they can take on any energy they want? Is that what it's saying? Yes, that's what it's saying. And we agree with it because there are no blank conditions. Yes! Boundary conditions. Because there's no boundary conditions, right? It's a free electron. There's no boundary conditions. That was just on the exam we're handing back, right? That's boundary conditions are why energy is quantized. I don't know if Jeffrey got that one right or not.
What did you say? Because there are no boundary conditions, electrons.
So then you can take on classical energies. There's no quantization because boundary conditions are the reason why there's quantization of energy. Okay. So unbound states it's called, or the continuum. Okay. Continuum sounds kind of more movie-like. Continuum states, ground states. Okay. This idea of shell will make sense in a little bit, I guess. Subshell. I don't know if you, we maybe aren't careful enough with our terminology. But when I say 3p, I'm talking about a subshell, right? I'm giving an N and an L. So I know that in the 3p, I have these 3 orbitals that are in the subshell. If I'm in the 4d, I'm also in a subshell because I specified my d, and I've got 5 orbitals in there. Okay, and they all have the same. They all have the same energy. These subshells all have the same energy or different energies. Right? There's 1s. Right? Because since we're talking about hydrogenic, right? The only thing that depends, the only quantum number that determines the energy is which quantum number again? N. So that's why 2s and 2p are exactly the same energy level. 3s, 3p, 3d, they're all the same energy level. Because hydrogenic only depends on quantum number n. Okay, so you have these subshells. Okay. But usually we think of subshell as just the L, but I guess with hydrogenic it can go a little bit further than that. Be a little more loose with our terminology. Boundary surfaces. Here they plotted out, do you recognize them? Which atomic orbitals, which one electron wave functions, which solutions, which quantum numbers, kind of saying the same question over and over, different ways. Which orbitals, which atomic orbitals? Do you recognize them?
What are you pointing to?
This.
I was like,
Sorry, this.
Okay.
This. Do you recognize those atomic orbitals, those one electron wave function probability densities? Are your eyes really good and you can see what that says?
Oh, P, Y, P, X, P, C.
They're the p orbitals. They're the p orbitals. Sometimes they color them different shades. And the reason why is the wave function is just changing sign. Here it's, I don't know, let's pick one. Light is always plus. Okay, fine. So that means the dark is always where it's negative. So a lot, instead of putting a plus and a minus sign, they just give them different colors. But for them to, for the wave function to change sign, it has to go through a node, and there's a node. I think it's best described as an angular node, but that's not on here. But those are angular nodes, not just any regular nodes. And it's kind of interesting too, I think, if we could scan and get some more pictures of orbitals on here, the number of those angular nodes is just L. So for p orbitals, L is just 1. So there's only one angular node then. Okay, there's only one angular node. The radial distribution function. Okay, so now we're starting to get into where things are at. This is the probability of finding the electron at R. So probably finding an electron at a distance r from the nucleus. So that's where this eggshell idea is coming in, right? That because it's spherical, so what's the probability of finding it this far away from the nucleus? Okay, it's kind of like an eggshell is what you're trying to find it in. Okay, this is all for a 1s orbital. That's what this plot is for. Okay. I think we need to talk about a few things here. If you want to find radial nodes, because the homework is going to ask about a few things. Radial nodes, what you do is you set this r function equal to 0. Oh, let's say, let's be specific, radial nodes for 2s. Well, you find this, and again, I don't have it scanned. You find in the reading, you find the radial wave function for the 2s. Set it equal to 0 and solve for it. Okay, again, this is just from a table. Table in the book. Okay. It's on, oh, I think it's on page 349. I'll show you what it looks like. Yeah, here's a bunch of them. Page 349. It's table 13.1. So someday I'll have this scanned and get it in there. Table 13.1. Okay. And there's all your radial wave functions. You just pick an N and an L, and then you just, page 349 is where they're all at. Set that radial wave function equal to 0, you can get the nodes. I think they're also going to ask for the extremes. I think they're also asking for the extremes. What are the maximum? What are the extremes? Now you gotta, what did I do here? Now you just take the derivative and set it equal to 0. Okay. And then I think there's one more possible question they could ask with this radial distribution wave functions. What was it? It was to find the most probable radius. To find the most probable. This is how you set up each of these three situations here. Now you take the derivative with respect to r of that p of r. Right? But that p of r is just, well, realize it's really just the derivative. I gotta just to make it more clear. The derivative with respect to r of, what was r again? What was p? P was r squared times the radial wave function. Right. If we're talking about 2s all the time, right? Just pretending it's 2s. So whatever orbital they're talking about, you just find the right the right distribution function and put it in there. So we talked about how these guys were in page 349, table 13.1. So finally, here's the full wave function. Here's our radial distribution function that we talked about. Then you have the angular portion, and that's your spherical harmonics. We talked about this last time, like with rigid rotors and things. That's in table 12.3. So you got to go back a chapter to get those again. Table 12.3 on page 334. So if you just specify an L and an M sub L, and then you can write the entire, well, in the orbital, I guess, you can write the entire wave function for hydrogenic atoms. Somewhere in here I was going to we stop here? I think I want to stop here and then do homework and stuff. So if we stop here, and then we'll pick up in the next class period the next part. So you don't have to do, you already did the words for the next part, so don't do words again. So on Monday we're going to pick up section 13.3. But that means you do homework through, oh, there's our tables. I did scan them. What a guy. Do you have these notes?
No.
Oh. Sorry. Okay. But there they are. Okay. And then you're going to stop here at this line. Okay. So we have this additional question here, though. It wanted us to write the wave function. So we'll start here. Let's start doing our homework here. It's going to copy everything. How can I do that? That's okay. Bring it down here. That's what we should do first. So we want to write the wave function for a 1s orbital. Okay, so how do you do that? Where did it go? Oh, here it is. I was looking right at it. Okay, so we need to look up the radial distribution function, the radial wave function, and the spherical harmonics. Multiply them together and we'll have our answer. What was that? I forgot. It's a Y. Okay. And we got this nice table here. You don't have to go look in the book. So they said for 1s, so for 1s, can you see it? It's going to be, yes. Good, so L will be 0, and it's also written over here. It's kind of redundant information there, but there's my R function. And this symbol right here, if you can see it, it says e to the negative rho over 2. And you hear it, here's where it says what rho is. Do you see that? That rho, if you can't read it, it's 2z, that's supposed to be a 2zr over a naught. That's what rho is. Okay. So let's put that in for our radial wave function. We've got 2z over a naught to the 3/2, right? You see I'm just copying this right here? And then I have to have e to the negative rho over 2. Might as well put it in what rho is. E to the negative 2zr over a naught. So all of that was my r.
It's all divided by 2, though.
Did I forget the 2?
The e to the rho over 2.
Oh, it is. Did I forget that, guy? So the 2's are going to cancel out on me. Thank you. Yeah. Okay, now the y part. What would I write for that? Can anyone read that?
First one? What is it?
Yeah, so where's the wave function though? The spherical harmonic you're supposed to write. It's just going to be what?
1 over 4 pi.
Yes. See that? That's just the part you write. Thank goodness, right? Otherwise I was going to get really ugly. Okay, so we're done with the first part. And then it said, okay, calculate the most probable radius. And to calculate the most probable radius, we said do what? Which one of these three cases are we really messing with? The third one, right? So we want to take the derivative with respect to r of that radial distribution function, p of r. So here's our answer. This is what we got to do. And we're doing for 1s. It should be set equal to 0, wouldn't you think?
Solve for r.
Yeah, how could it has to be set equal to 0. Otherwise we're not going to be able to get rid of stuff. Yeah. I think this guy right here should be this, but set it equal to 0, right? Determine the most probable radius. It's got to be set equal to 0. Oh, I don't see how you do it. So we need to set this equal to 0. And then solve for our r. Now, does this look familiar?
Use the same r from the wave function.
Well, this R1s is going to be this guy.
Mm-hmm.
But I'm saying, does this look familiar?
Yeah.
But it looks like we're using the
I think we did this in the concept preview.
r equals 0 and k naught.
Yeah.
Oh yeah, but it was like 4z over something. 4z over a naught, I think, because we just completely took it out.
And you can here too, because, right?
Yeah.
So just, you already have an idea how to do this, so I think you can do that. This is a you do then. And you should come out with a naught, it seems to me, because that's the whole definition of a naught. Okay. Let's see if we can set up a exercise. So now I'm here. A exercises 1 and 14. Oh, yeah, these they're typed up. It's a lot bigger so you can see it. Okay. Here's the first one. When ultraviolet radiation of wavelength 58.4 nanometers from a helium lamp is directed onto a sample of krypton, electrons are ejected with a speed of 1.59 times 10 to the 6 meters per second. Calculate the ionization energy of krypton. And you're doing good if you remember what this kind of thing is called. Somebody's effect. Or not, I guess it wasn't somebody's.
The photoelectric.
The photoelectric effect. Okay. Now you can either try to remember the relationship we had for that or just kind of figure out on your own. They want the ionization energy. Okay, fine. How much energy do you have to work with in the first place in this process? Not conceptually, not an answer. Just how much energy do you have to work with? The energy of the what?
Photon.
The photon. That's your total energy, right? So before and after, you have to have energy conservation. So you have the energy of the photon. That has to equal what? The after process, and the after process is the end product. So you start out with the energy of the photon. Well, that number of joules has to equal, more specifically, energy of the electron. Because what type of energy is that? Kinetic. So you have the kinetic energy of the electron. And what other hunk of energy had to get sucked up? Otherwise, it's not going to get kicked out in the first place.
The work function?
The work function. We called it the work function. Here they're calling it the ionization energy. So the energy of that photon has to equal the kinetic energy of the electron plus the ionization energy. Or think of it this way, right? Maybe think of it. Maybe put ionization energy first, because that has to happen first. It really doesn't matter, right, mathematically, but the energy of that photon has to go into the ionization energy, and then what's left over all goes into the kinetic energy of that electron. Because remember, there aren't any boundary conditions. Whatever energy is left over, that electron will take on. So do you see how to do this? Alyssa, what was the equation for kinetic energy again?
This is 1/2 times mv.
So close, 1/2 mv squared. So that's this part, exactly. You're going to solve for this guy. What do you put in for this?
HC over lambda.
Ooh, good. Just watch your units, right? HC over lambda, just watch your units. That was, I always lose track of time. We're supposed to,
We were supposed to stop like 3 minutes ago.
fine, Gloriana.
Now it's 5 minutes ago.
Yeah, it was 5 minutes ago now.
All right, so you can probably handle the rest of these.
So we don't hold
Right.
the node in
No, we stop at the line.
on the line. Oh, there it is.
Oh, you don't have that either, do you?
No.
No, we do. We do have one.
Oh, you do have a line? Okay. All right. I should probably, I'll email this out to you, because then because maybe there's other changes besides this, right? That'd be nice to have those tables. Does yours look like this for the next day 3?
Day 3.
Do you have colored pictures and stuff?
Oh, look at this. It's all empty.
It's changed a lot. It's changed a lot then.
We paid $30 for an empty.
Paid $30 for the wrong notes.
Yeah, well, you get what, I guess you didn't get what you paid for.